Hi, welcome back to AP Physics C, Electricity and Magnetism, Unit 2, which is conductors, capacitors, dielectrics. So in the first two videos, we looked at the electric field of a conductor, and then we looked at the electric potential of a conductor. Now let's look at capacitors, okay? So conductors, that part of conducting, the conductors really ends kind of the electrostatics portion of the course. Now we're going to start talking about circuits, of which at some point in time we're going to address what is called an RC circuit, which is a resistor capacitor circuit, okay, which is what most of the circuits that we see in electronics and so forth are. They're RC circuits. So what is a capacitor? So a capacitor is a device that can be used to store charge and electric potential energy. And what we do is we store the charge for later usage, right? Once we decide to discharge it. In a lab setting, you may use what's called a Leyden jar, which is what you see here, right? So this is a Leyden jar. You've got two pieces of metal, right, with a glass container, and you simply put this metal in, right, charge it up, and then, and then you can release it by touching this little kind of handheld thing, right? It would actually go up to that metal piece, right? It looks like a little hook. Right, and then you'll see like a little bolt go across. So there's a little lightning piece goes across. Defibrillators, right? The charge, right? Well, what they're doing is the doctor or the EMT who's using it is going to tell them to charge it to so many volts. Well, what it is on the inside, there's these capacitors that are working that are starting that charge, or that are starting to store that charge. And then once you hit the buttons, it's like taking that piece of the Leyden jar and connecting the two metal ends, then you release it, okay? And the reason why they tell you to clear is because our bodies have electric circuits all over the place. You don't want cross contamination of circuits. So as the electric charge is trying to go through one body, to the heart, you don't want to touch it because it will pass through your body as well, right? So every capacitor has what we call capacitance, which is measured in farads, and that's named after Michael Faraday. And the equation for capacitance, and you can see here in the definition, is the ratio of charge to potential difference is what we call capacitance. So the ratio of charge to electric potential. But you more commonly see it written for charge, which would be Q equals CV. And that C is the capacitance. Okay. Now, the most common capacitor that is studied in AP Physics C and really in all electricity and magnetic courses is what we call a parallel plate capacitor. And the way a parallel plate is set up is that you have two charge plates of an area, right? And then you have an electric, circuit attached into an electric circuit. You have one plate that's positively charged, one plate that's negatively charged, which means we have an electric field that is going through here, which means if we have all this happening, we got a voltage, we got an electric potential, we got a potential difference, we got energy, right? We have all this stuff running through, and the main thing is we're going to look at, right? What really focuses on the capacitor is the area of the plates and then the distance between them. Now, that area could be a square or a circle. Right, you see both questions pop up, okay? What you see down here with the cylinder, this is a very special case. We'll actually do this in an example problem. Now, the electric potential between the two plates can be calculated by simply doing V equals QD divided by epsilon naught A, right? And so, in fact, I should have put this next bullet point before this one because the capacitance in relation to distance and area is epsilon naught A over D. Okay, and then if you take this, plug it in there, and do a little bit of algebra, you end up with that QD over epsilon naught A. And of course, we're talking about storing. So how do we calculate how much energy is stored on a capacitor? Well, it's simply U equals 1/2 QV, but then you can go through a line of algebra and end up with two other equations, which is 1 over QV, right? 1 over charge times voltage, or 1/2 charge times voltage, but that's also equal to 1 over capacitance times voltage squared, or charge squared over 2 times capacitance, okay? And epsilon naught is that vacuum permittivity, and it has a value 8.854 times 10 to the negative 12, okay? And so that K value is 1 over 4 pi epsilon naught, where we would take this number, plug it in there, and that's how you get that 9 times 10 to the ninth. All right, so let's look at some example problems. The first one is very quick, very short, very simple. The second one is a little bit more involved, right? The second question is centered around this this cylindrical parallel plate capacitor. All right, so here we have a parallel plate capacitor of 10 centimeters by, it's a square, so 10 centimeters a side, separated by 1 millimeter. We're going to calculate the capacitance of this device, and then if we charge it to 12 volts, how much charge is transferred from one plate to the other. Because remember, that's what the E field does, is it transfers electric potential, right? So part A is very simple. To find the capacitance, we just do epsilon naught A over D, right? And so we would do epsilon naught side squared over D, because that's our area, right? It tells us it's a square. So we do 8.854 times 10 to the negative 12th times 0.10 squared. Don't forget to square that because that's the side. And then we divide it by 1 times 10 to the negative 3, right? So we have to convert those millimeters to meters, the centimeters to meters as well. And so that's going to tell us it has a capacitance of 8.854 times 10 to the negative 11th newtons per coulomb. Oh, sorry, not newtons per coulomb, farads. Sorry, I was using red. Sometimes you'll see this written as picofarads, right? So you would divide this by 10 to the negative 12th, and it'll tell you how many picofarads there are. All right, part B, right? So as the capacitor is charged at 12 volts, how much charge was transferred? We would use Q equals CV, because that's the charge we're looking for. So we would say 8.854 times 10 to the negative 12th times, not negative 12th, negative 11th times 12 volts, and would give us a charge of 1.06 times 10 to the negative 9th coulombs. Okay, there is a second way to do that. This problem, we would use the voltage. Sorry, let me go back, and so it's QD over epsilon naught A, and then solve it for Q, which you actually just end up with that CV in the long run, because basically you're taking this and plugging it into there. Okay. Now let's look at the one that's a little bit more involved, right? So this is a cylindrical parallel plate. So the way we want to do this is we want to attack it as such. First thing is we're going to use Gauss's law. Okay, and what Gauss's law will allow us to do is find the E field, right? The magnitude or an expression for the E field. The second thing we're going to do is we're going to do define the potential difference by doing the integral of EDR. And then finally, we're going to plug it into the equation Q equals CV, or we can solve it for C right here. So C equals Q over V, but we're going to leave that Q alone, right? Because that's going to be the charge that's enclosed by our Gaussian surface. And then you're going to see it pop up from our E field calculation, and then you're going to see it from our integral as well. Now, so let's start attacking this, right? So let's start talking about Gauss's law, right? So what we're going to do is we're going to put a cylinder in here, right, of length L, capital L we'll call it, of radius little r, okay? And so that's going to be what our Gauss's law, but we need to figure out the charge inside this capacitor, right, or the charge inside our Gaussian surface. And so what we're going to do is Q inside is just going to simply be the ratio of length, the two lengths, right, times Q. And so this L is our Gaussian surface. This L is our parallel plate capacitor, okay, the length of those. And then we're going to now use that for our Gauss's law process. So we would just simply do Q enclosed, or what we call Q inside, is equal to the integral of E dot dA. But again, our line of, to get down to EA. Now this is a cylinder, so the surface of a cylinder is 2 pi r L, right, times E. But this R is the radius. These two are for the Gaussian surface, not the actual cylinder. That's why I'm using the capital L. Okay, so I'm going to solve this for E. So E is going to be Q enclosed, or what we call Q inside, divided by 2 pi r capital L little l E. But now Q enclosed is this ratio of L over L times Q. So I would say L over little l Q over this 2 pi r L E. Well, I can do some algebra here. Cancel, cancel. And so I end up with Q over 2 pi r L E. So this is my E field. That's not E. Why did I put that E in there? It's epsilon, not E. All right, so that's my E field inside my Gaussian surface caused by the central object there. Now I'm going to do the second thing, which is I'm going to find the expression for the voltage, which is going to be EDR. Okay, and I'm going to evaluate that from R1 to R2, right? The gap between these two, right? Or from the middle cylinder out to the other plate. Okay, and so now I'm going to do my E field, but constant, 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 constant. So the only thing that's not constant is the R. So I'm going to pull all that out in front. So Q over 2 pi L epsilon naught, the integral of 1 over R dr, evaluated from R1 to R2. Okay. In fact, when I say evaluate from R1 to R2, right, I'm going from edge. That's allowing me to go from edge to edge. So it's just that gap there. Right. Well, 1 over R is natural log. Right. The integral of 1 over R is natural log. So I've got Q over 2 pi epsilon naught L times the natural log of R. And I'm going to evaluate that from R1 to R2. And now here's the reason why you learn those log properties in Algebra 2, because this is going to be ln R2 minus ln R1. Well, that just becomes ln of R2 divided by R1. Shout out to all those Algebra 2 teachers who now know why we teach all this natural log and log stuff. So my electric potential is going to be Q times 2 pi epsilon naught L natural log of R2 divided by R1. Okay, so now that's what I need, because now I do C equals Q over V. Right, so now I'm on to step 3. So step 3 is plug all that into Q over V, and so it's going to be, I went backwards. So it's going to be Q divided by this mess. Okay, so this last part is actually times, right? It's not in the denominator with the 2 pi epsilon naught L. Right, and so I can do algebra. Q goes away. This goes up into the numerator, and this stays in the denominator. So the expression for capacitance of a parallel plate or cylindrical parallel plate capacitor is going to be 2 pi epsilon naught L, which is the length of the cylinder, divided by the natural log of R2 over R1. And so there is the capacitance of a cylindrical capacitor, right, of 2 conductors. So in the next video, we're going to finish out the chapter, or the unit, I keep saying chapter, but we're going to finish out the unit by looking at dielectrics, which are essentially a capacitor plus something else.